Okay, so welcome everybody to the PRIISM seminar today. I'm really excited to welcome Dr. Christina Knudson. Dr. Knudson is an assistant professor of statistics at the University of St. Thomas. She earned her PhD from the School of Statistics at the University of Minnesota in 2016. And her research focuses mostly on statistical methodology, with two of the main topics being generalized linear mixed models and MC-MC sample analysis. And she also maintains the R packages GLMM and stable GR. And so with that, Christina, if you want to share your screen, we can get started.
Excellent, thank you. Okay, so I'm guessing that as like mostly practitioners, you're probably pretty familiar with the Gelman-Rubin Diagnostic, but if you're not, that's totally okay. I'll review it a bit. And today we will be like revisiting this diagnostic, improving it, and how we implement it. And this is joint work with my collaborator, Dr. Dutika Vats, who's at IIT Kanpur. But when we were doing this research, she was at the University of Warwick. Okay, so first of all, just like, what's the big picture? What are we doing here? We're using Markov chain Monte Carlo to approximate some target distribution. Lots of times this is in the context of Bayesian statistics, and we have maybe an intractable posterior distribution, but it doesn't have to be Bayesian statistics. We could just have some target distribution that we are trying to approximate with MC-MC. All right, so we know that we run this Markov chain to sample from this distribution, and then we get an approximation of that distribution. But the question when we're actually doing this is, how long do we need to let this chain run? So more precisely, after the chain has started sampling from the target distribution, how long should we let it continue to run to produce a decent approximation? One of the tools that has been developed is the Gelman-Rubin Diagnostic, and there are lots and lots of diagnostics, but this is probably one of the most popular, one of the most frequently used diagnostics for deciding when to terminate a Markov chain. So the basic idea of it is that a practitioner would run parallel chains, independent chains, with over-dispersed starting points. So that would help you hit many different areas of your target distribution with those over-dispersed starting points. Then we calculate this thing called R hat. And once R hat hits the predetermined threshold, then we can stop. Okay, so what does R hat look like? It is the square root of sum of two ratios. So the first ratio here, chain length minus 1 over chain length, that is not a very interesting ratio. Obviously, as the chain gets longer, then this first ratio is just going to go to 1. So this part is boring, but over here, this is the more interesting part of the R hat. So this part of the R hat looks at the between chain variance divided by the within chain variance. So if we think about like when we just let our chains run for a few steps, since we've started them pretty far away, the between chain variance will be pretty large. But since they won't have moved very much, these chains, then the within chain variance will be pretty small. So our numerator is going to be big. The denominator is going to be small, meaning that this fraction is going to be large. And so R hat will start big. And then as you let your chain run longer and the chains explore more of the target distribution, then this second ratio will decrease, eventually approaching 0. This first ratio will approach 1. And so R hat will decrease down to 1. Okay, so we will not let it go all the way to 1 because that would take infinitely long, but we will choose some thresholds that when it gets close enough to 1, then we can say, okay, good enough, let's terminate our Markov chains. Okay, so the big question, of course, is how long is long enough? So in other words, how long do we need to let this run in order for R hat to be close enough? Like how close is close enough? From 2004, Gelman's book with his collaborators or co-authors, he says, for most examples, values below 1.1 are acceptable, but for a final analysis in a critical problem, a higher level of precision may be required. So we can see that this value 1.1 is provided as kind of guidance. There's no like very hard cut threshold for like a more critical problem though. So what we have done, my collaborator and I, is we just looked at a whole bunch of papers that were published in 2017 that used the Gelman-Rubin Diagnostic for terminating their simulation. And here are some of the values that they used for terminating their simulation. One person or one paper used an R-hat of 1.003. Another 12 papers used 1.01. And then we have kind of some seemingly arbitrarily chosen values in between. We have 43 of the 100 papers used the suggested 1.1 value. And then we have 10 papers that used values above the suggested 1.1 threshold. So we can see that there's a good bit of variation in the R-hat thresholds that have been used. It looks like a lot of people got the 1.1 memo, and also several people have gotten the memo about like a more critical problem. So we may wonder, like, this person who's used 1.003, that looks like pretty good in comparison to the rest of the papers because this is the smallest threshold used. But like, how good are these thresholds? Are they good enough to be like producing reliable results? Okay, so what my collaborator and I did is we just started 3 chains and we sampled to approximate just a simple t-distribution with, I think, like 5 degrees of freedom, if I remember right. And we let these run until we got an R-hat of 1.005. So we chose this R-hat that was smaller than 99% of the papers that we just saw on that previous slide. In the light gray, we have the individual chains. So we have 3 estimated densities because we had 3 chains. We had in the red dotted line, we put the like 3 chains estimated densities together to produce the one estimate in the red dotted line. And then the black solid line is the true density for the t-distribution. So what we can see is even though we ran our chains so that we got an R-hat of 1.005, and even though we're working on a very simple problem, just estimating a t-distribution, we have a pretty bad estimate. This red dotted line is not looking like a very good estimate at all of the black solid line. So I would say that this R-hat was probably not small enough. And if we think about 1.005 compared to 1.1, if this is how bad 1.005 looks, then it would probably be a little bit frightening to see what the estimate would look like if we had stopped at 1.1. Okay, so what my collaborator and I have done is we sought to improve the Gelman-Rubin diagnostic in 2 ways. One of the ways is we stabilized the Gelman-Rubin statistic, that R-hat. And then the other way that we have improved the Gelman-Rubin diagnostic is we have improved the implementation of it by, instead of using R-hat less than 1.1 as a threshold, we've constructed a more principled interpretable threshold for terminating the simulation. And we'll see this is based on effective sample size. Okay, so the 2 things, we'll go into stabilizing the Gelman-Rubin statistic first. And the basic idea of this is that we're just trying to do better variance estimation. Okay, so if we just look again at this R-hat statistic, remember we have this first ratio that's boring, and then the second ratio is the between chain variance divided by within chain variance. So we can see that we have 2 variance calculations, and instability in either one will then produce instability in this overall R-hat. So in particular, the thing that is producing a lot of instability in the original Gelman-Rubin statistic is the between chain variance, the numerator of this second ratio here. So instability in this creates instability in the entire statistic. So what we're going to look at first is why is the original Gelman-Rubin's between chain variance unstable? And then we'll look at how we have stabilized it. Okay, so if we just have some Markov chains, we have the ith one, the ith chain, and we could have maybe one chain or we could have multiple chains. Or rather, we need to have multiple chains in the original setting. And then we'll have the teeth step. We just define a couple means. The grand mean is this mu hat. And then the ith chain's mean just averages over all the steps in the ith chain. So we have x bar I dot and then the grand mean mu hat. All the original GR estimator does is calculates between chain variance by looking at the these means for each chain and then just takes the variance of those means. So here it is like in equation form, we're looking at the variance of those chains means. And of course, like usually when we're doing Bayesian statistics, we don't usually run a whole lot of chains. Usually we try to run like a reasonable amount of chains, like 3 or 5 chains for longer so that we can explore kind of more space that way. So since we may usually run only like 3 or 5 chains, then that means that we're calculating variance based on like 3 or 5 numbers. And so this variance is not going to be very stable because obviously we all know like 3 or 5 data points is not that many data points. So this original between chain variance we can see is going to be pretty unstable, pretty variable since the number of chains we run is so small usually. Okay, so if we look again at this between chain variance estimator, here it is. If we have any like background in MCMC, more like kind of theoretical research, then we know that this is just the variance of the MCMC means. And there's actually a whole lot of research that has happened in the last 30 years since the Gelman-Rubin Diagnostic first came out. So what we decided to do is just leverage the last 30 years of variance estimation literature. So there are a whole bunch of different meaning better variance estimation techniques. And pretty much you could choose any of the ones that have been established in the last 30 years, and it's going to be more stable than the one that Gelman and Rubin used in their original diagnostic. So lots of different options. The one that we used in our improved implementation is the log-sale batch means estimator. Now, the most important thing is to have a more stable variance estimation technique. But we chose this particular improved more stable one because it makes termination a little bit more conservative. Meaning that we'll just make the chain run for like a little bit longer. So big goal is improved stabilization, and then kind of cherry on top is making the termination a little bit conservative, making it run just a little bit longer. Okay, so what is the log-sale batch means?
Christina, can I ask one quick clarifying question that was raised in the chat? So the question is, most chain variables X are multidimensional. What observables do you use besides components of X?
We will get to the like multi-dimensional stuff in like a little bit. So maybe we'll like revisit this. How about the person can re-ask if there's still a question in like 20 minutes?
That sounds great. Thanks.
Okay, cool. Okay, so log-sale batch means big goal is improved stability. Nice thing is it makes termination a little bit conservative because we're tending to overestimate the between chain variance a little bit. So because we're overestimating this between chain variance a little bit, then that means that R hat is going to be a little bit inflated. And so that will mean that in order to hit that threshold, then we need to run the chain just a little bit longer in order to get R hat below that threshold. Okay, so if you are doing some Bayesian modeling and you have a bunch of output from your chains, then you can run this stable.gr on your output in order to get your R hat calculated using this log cell batch means estimator. Okay, so I have told you that the log cell batch means estimator makes this more stable, but let's see, let's like, prove it to ourselves with some plots in a simulation. So all that we've done in this very first simulation is kept it pretty simple. We just ran an AR1 process. The teeth step is equal to 0.95 times the previous step plus some epsilon term, and the epsilons are normal 0, 1. And so since it's an AR1 process, then that's actually just the same thing as a Markov chain with this distribution here. So we ran 500 replications in this simulation. For each replication, we ran 5 Markov chains, and we ran them until our hat hit this threshold, which for now will look like mysterious, but in like 10 or 15 minutes, it'll make sense why we chose this weird looking threshold. So we ran these 5 Markov chains until we hit this weird looking threshold, and we ran it according to 2 different criteria. 1, we terminated when the original Gelman-Rubin R hat hit the threshold, and 2, the other one, we ran the chains until our lug-cell based R hat hits this R hat less than 1.001625. Okay, so same threshold, but just 2 different calculations for R hat. Okay, and here we have the results. Down on the x-axis, we have the number of iterations until the chains converged. And we can see that like some chains converged after 10,000 steps, some chains converged after 30,000 steps. And then up on the y-axis, we have the sample mean at the time of convergence. So at the time of the simulation being terminated. The blue dots represent the sets of chains that were terminated according to the original Gelman-Rubin diagnostic. And then the green points, more in the middle, are the points associated with the chains that were terminated according to the more lug-cell based R hat. So what we can see is when we terminate according to the original Gelman-Rubin diagnostic, we are sometimes terminating after like 2,000 steps, sometimes terminating after 35,000 steps. There's a whole lot of variability there. And it would be ideal if like when you ran it one time on a Monday with one set of random numbers, you would get something similar to if you ran it on Tuesday with a different set of random numbers. The green stuff, the green points here in the middle are much more similar from run to run. We are pretty close to like 12,000, maybe 15,000 iterations until we hit convergence. And since we have like more stability in the number of iterations to convergence, and that also means that we have more stability in the resulting sample mean as compared to the blue dots, which when we ran it for shorter, then we have a lot more stability and we have to run it for longer. We have a lot less stability when we run it for shorter. We need to run it longer to get more stability. Okay. We see this like dotted vertical line here. That represents, since we're working in this AR1 setting and we know the true variance and we can calculate the number of iterations until it should converge, until it should hit that R hat. This would represent like the number of iterations until we should hit that R hat according to the true between chain variance. And so what we can see is like the green dots are pretty close to that vertical line, but just a couple 100 or 1,000 iterations afterward. And again, that's because we said that we chose the lug-cell batch means variance estimation technique because it just slightly overestimates that between chain variance, which we said would make our hat a little bit inflated and make the chains run a little bit longer. Okay, so if you are doing some Bayesian modeling, then using this stabilized between chain variance will have a huge effect in stabilizing the number of iterations till convergence and the resulting sample mean. Okay, so now we have talked about the stabilizing the variance estimation, and we said that the second thing that we worked on was improving the threshold for terminating a simulation, because we saw that using r hat less than 1.1 was maybe not the best thing. We think that we can improve that. So the way that we improved it is we looked at effective sample size. An effective sample size, if you need a refresher, that's just the number of uncorrelated samples that produce the same precision as the correlated or MCNC sample. And in particular, when we look at the R hat formula, we recognize that the second ratio can be rewritten instead of between chain variance over within chain variance. We could just rewrite it as the number of chains divided by the effective sample size, the estimated effective sample size. So most importantly is we have this one-to-one relationship between effective sample size and R hat. Okay, so what does this mean? Why does this matter? This means that now, all of a sudden, our R hat threshold is interpretable. Because if I tell you the R hat is 1.005, I could go look at how long you ran it and the number of chains you had and say, okay, well then that means your MCMC sample has an estimated effective sample size of 250 or whatever. And similarly, if you say, I want to have an effective sample size of 300, then we could go out, punch in your number of chains, and then approximate this with 1, because this will go to 1 like as you run your chain longer. And we could find our desired R hat. Okay, so our R hat threshold is interpretable, and it can be calculated before running anything, like I just said. So this is pretty similar to like in an intro stat class, how you ask your students, okay, if I want to have a confidence interval that's no wider than whatever width, what sample size should I use? This is pretty similar to that, and there's already research about calculating this effective sample size. So what we just did is leveraged that research on calculating estimated effective sample size and used that to then, before anyone does any like sampling, go out and calculate the target R hat threshold. So now before you like go out and sample, you can go ahead and figure out like what will be our threshold for terminating simulation. What is this R hat that we're going to use in order to have a large enough estimated effective sample size? Okay, so in our R package stable GR, then the command for finding this goal threshold, this target R hat, is target.psrf. And then to find the estimated effective sample size, that's just n.eff, so the effective sample size there. Okay, so let's see how this principled threshold works in practice. And what we did is we have just looked at the data from the Titanic, and we're modeling the log odds of surviving the Titanic. So this is just a Bayesian logistic regression, and we have the following predictors. We have the fair class, which is categorical with 3 categories. We have the gender of the people on board, 2 categories, since that was how data was collected back in that day. We have the age of the passenger, which is quantitative. And then for each passenger, we have like the number of siblings and spouse aboard. So if you're on board with 2 siblings and then your husband, then that would be 3. And then also we have the number of parents or children on board, and that's also quantitative. Okay, So those are our variables plus the port of embarkation, or where they boarded the Titanic. So we ran a Bayesian logistic regression with those predictors. And in this simulation, we had 100 replications. For each replication, we ran 5 chains until convergence was diagnosed according to 2 different things. One according to the threshold of 1.1, and then also separately according to the ESS-based R hat termination threshold. And just to like hone in on the difference in the thresholds, we use the same Lugsail-based R hat calculation for both of these 2 termination thresholds. So same calculation, just when do we stop? Are we stopping according to R hat less than 1.1, or are we stopping according to the ESS-based termination threshold? Okay, so here are the results. Down on the x-axis, we have the different components. So the first component is the intercept. Then we have the second class passenger coefficient. We have the coefficient on the third class passengers. We have the coefficient for male. We have the coefficient on age, the coefficient on the number of siblings and spouses aboard. We have the coefficient on the can't remember what that means. Parents and children. And then the coefficient for the fare that they paid, the coefficient if they embarked on Queenstown, and the other embarkation point. Okay, then for each one of these, like if we just look at, for example, the sibling spouses one, we have 2 sets of points. The left set of points, the like ones that are a little bit more spread out, those are the points from terminating according to R hat less than 1.1. And then the right set of points, which are more tightly packed, those are the points from the runs that were terminated according to the effective sample size based R hat threshold. And then each one of these little circles represents one run of our one replication of our simulation. So each point represents one set of 5 chains that were run until hitting this R hat less than 1.1, or until hitting our R hat less than the ESS-based threshold. Okay, so what we can see is that we have a lot more variability in all of the left sets of points. So for the intercept, the left sets of points have a lot more variability. For male, the left set of points have a lot more variability. All across the board, with maybe the exception of fare, because the scale is so small, all of the left sets of points have a lot more variability, meaning that when we terminate according to the R hat less than 1.1, we have a lot more variability in the coefficient estimates. This is not ideal. If one of you runs a model with one set of random numbers and another one of you runs a model with a different set of random numbers, you would like to get similar coefficient estimates, right? So running this according to R hat less than 1.1 is probably not the best thing you can do. Instead, running it according to R hat less than this effective sample size base threshold is going to give you much more stable coefficient estimates. Okay. Also in this plot, we can see we have 3 sets of colors. We have purple dots, blue dots, and green dots. The blue dots are the posterior means. And then the green and purple are the endpoints of our 95% credible intervals. So the purple is the upper endpoint of our 95% credible interval. The green points are the lower bound of our 95% credible interval. So what we can see in this is The blue dots like do have variability, more variability in the left set of points than the right set of points. But when we look at the 95% credible intervals, that's where we see a lot more variability coming in the left set of points. So for example, if we look at like this second class coefficient, the purple dots in the left set of points have a lot more variability than the purple dots on the right set of points. And again, that's just because running until we hit r hat less than 1.1 is going to be not as good. It's just going to produce like less stable credible intervals than if we ran until we hit that ESS based termination threshold. Okay. Okay, so we can see that there's definitely an improvement in the stability when we use this other threshold instead of 1.1. Now let's see like how that feeds into the resulting predictions. So if we remember the movie Titanic, there's Jack and there's Rose. We just plugged in what we understood about them, like where Rose embarked, where Jack embarked, how many spouses and such these people had aboard. And then we just, using these coefficient predictions from back here, we plugged in their values and produced their probabilities of survival. So on the right, we have the probabilities of survival according to the simulations that were terminated according to r hat less than 1.1. And then the left, we have their estimated probabilities of survival when we terminated the Markov chains according to the effective sample size based termination threshold. And so no surprise, like back here, we had a lot of estimation of the coefficients that then propagates forward into our probabilities of survival. When we terminate according to 1.1, then we have a lot greater variability. And of course, we would like to have as little variability as possible. So it would be wise to, instead of running your chain until you hit r hat less than 1.1, it would probably be wise to run your chain until you hit the effective sample size based r hat. Okay, so I said that we would talk about the multivariate stuff, and we will go into that now. So the r hat statistic that I showed you before, with that ratio of between chain variance on top, within chain variance on the bottom, that was for if you just had a single component or a single predictor. Now we are going to just talk a little bit about if you have a multivariate Markov chain. So the changes that we make are pretty similar in the multivariate case. First, like let's think about how Brooks and Gelman, who did the multivariate r hat, how they thought about the between chain variance and the within chain variance. So with Brooks and Gelman, their within chain variance was pretty much the multivariate analog of the within chain variance from the single component setting. We have just the sample covariance matrix for the ith chain, and then they just took the average of those sample covariance matrices. Okay, so just the average of the sample covariance matrix represented the within chain variance. And then for the between chain variance, they used a pretty similar, like the multivariate analog of the between chain variance from the univariate case. So just looking at the average chain, this is xi dot is just the ith chain's average, and then looking at the variances of the variance of those chains means. So they then called that B over N, and now we can go back to remembering that the univariate r hat has between chain variance divided by within chain variance, but of course, like a sample covariance matrix is a matrix, and what does it mean to have one matrix divided by another matrix? So instead of doing like just division, which wouldn't make any sense. What they did was they looked at S inverse, which was S was the within chain variance estimate. And then B over N, remember, was the between chain variance estimate. So they looked at S inverse times B over N. And like at this point, this is still a matrix. We need to now like make this into some kind of scalar. So what they did was they looked at the maximum eigenvalue of S inverse times B over N. Okay. Sorry. Okay, so they looked at the max eigenvalue, and what does that mean? If you use the max eigenvalue, then that means that this R hat is going to be controlled by the slowest converging linear combination of components. So it would be one thing if this was controlled by like the slowest converging component in your Markov chain. Like that would be slow, but maybe more okay. But it's even worse than that. It's the slowest converging linear combination of components. So it's the slowest converging direction. And that means that R hat is going to be unreasonably high in practice. Especially if you have a large number of components, then we can just imagine like, yes, finding a linear combination that's in the worst direction, the slowest converging direction, will just make R hat unreasonably high. And so that's, I think, why lots of times in practice, you don't really see people using the multivariate R hat, is just because it's so ridiculously slow to converge. So even with this threshold that people have been using of 1.1, people don't really use a multivariate R hat, especially in the like high dimensional setting, just because it's going to be so ridiculous, requiring you to sample for so long in order to hit convergence. So I think that's why lots of people just look at like each component's univariate R hat and then do something based on that. So what we did is we saw, okay, we can do better than the slowest converging linear combination of components. We can do better than the maximum eigenvalue. And we can improve the between chain variance calculation. So just like the between chain variance calculation was improved in the univariate setting, we just did the exact same improvement in the multivariate setting. The log scale batch means estimator works pretty much exactly the same way in the multivariate setting as the univariate setting. So we implemented that log scale batch means variance estimator. And instead of looking at the max eigenvalue, because that is saying the slowest linear combo of components, the slowest converging linear combo of components, we used the determinant because that better represents the joint convergence of the components. Okay, so we looked at the joint convergence by looking at the determinant, and we improved the variance estimator so that it would be much more stable. So we've stabilized it and made it just like not super inflated, not looking at the slowest converging linear combo of components. Okay, so to like conclude what we have done, we stabilized both the univariate R hat and the multivariate R hat. And we did this by improving the method of variance estimation. In our particular implementation, we use the log scale batch means estimator because it's most importantly stable, but also because it will overestimate the variance a little bit, which makes R hat a little bit conservative. But as MCMC variance estimation improves, we should continue to update R hat to use like the best variance estimation techniques. So we're not saying like, use this, be done with it, use this until like 2072 or anything like that. We're saying keep improving it with new variance estimation techniques going forward. Also, we identified this one-to-one relationship between effective sample size and R hat. And because we were able to see that, then we were able to make R hat interpretable. Rather than just having R hat less than 1.1 be an arbitrary number, we could say R hat less than 1.1 is the same thing as running this until we have an effective sample size of 14 or whatever number. And because we can make R hat interpretable and ESS based, what we've done is leverage the ESS literature to create ESS based stopping rules so that we can replace R hat less than 1.1. And most of the time that means running it longer, which then produces better coefficient estimates. And then finally, like the multivariate R hat, rather than looking in the direction of slowest convergence, we made the multivariate R hat represent joint convergence by looking at the determinant rather than the max eigenvalue. Okay, and then mostly the point of this talk was to like convince you to use these better methods in order to stabilize your coefficient estimates and stabilize your predictions. So like the code itself is from your perspective as the practitioner is like pretty straightforward. There's like not really anything too challenging going on for you as the practitioner because we already like programmed it all up. But here's just like a baby example. So library stable GR, we just set the seed to whatever our favorite number is. Maybe like 5 components. Well, okay, let's make it 10 components. And then we chose a sample size of whatever you want it to be. Let's just do 1E4 for now. And then a matrix. I just changed this to, let's go back to 2 because I already have a matrix set up for 2 parameters, for 2 coefficients, or for 2 components. Okay, so I just set up a matrix there for the variance, and then just ran a few Markov chains, just ran 3 chains here. I'll just take a second because my computer is kind of slow. But this would be like where you're actually running your model and running your MCMC. And then once you have those chains, just put them in a list. And then just run the stable.gr function on that list of chains. Okay. My computer is like slow because it's just a baby laptop. Just give it a second. Okay, finally. Okay, so we ran our chains. There are our chains, put them in a list, and put them into stable.gr. And then here's what it outputs. Tells you the PSRF, or the R hat. So here's the R hat for the first component. Here's the R hat for the second component. But we are in this multivariate setting. We have these 2 components. So here's the multivariate R hat, which remember is the determinant. So here's our multivariate R hat. And then also here's our means, or our sample means. So here's the mean for the first component. Here's the mean for the second component. Here's that effective sample size that I was talking about. So it looks like running the chains for 1E4 is the same as producing an effective sample size of 17,592.71. And then if we look at n.EFF, so that will tell us just like our effective sample size. So again, it tells us our effective sample size, and then it tells us if we have converged according to that target.PSRF. So it says, yes, we have converged. And then also like beforehand, before you do any, before you run your MCMC at all, you can look at this target.PSRF command. And the first thing you put in is the number of components. So in this little baby example here, we have 2 components. And then Here we ran 3 chains, so we have m equals 3. And then kind of similarly to how, like, for a confidence interval, you can say, like, I want to be 95% confident, or I want to be 99% confident. And then you, like, build your you do your sample size calculation based on that level of confidence. Similar to that, we have, like, a couple more things in there, which are just set as defaults. And we can see, okay, if we have 2 components and we're going to run 3 chains, our target multivariate PSRF should be 1.000199. And that would be what you would then target. Okay, so I think that then concludes everything that I wanted to show you today. If you have any questions, definitely feel free to ask now, or you can send me an email later. And then also on my website, there's a link to the paper. For now, the paper's on archive. It's been accepted to statistical science. And then the R package stable GR is on CRAN, and then it's also on GitHub. So you can look at it either place. And I've got links to both those things here. Okay, thank you.
Thank you so much, Christina. I'll sort of do the round of applause. So yeah, just let's open it up for questions. Feel free to unmute yourself and ask anything.
Hi, I'm the one with the multivariate question from before. I wonder if your effective sample size thing, I know you didn't, there's a big literature that you're referring to, but is it based on estimating the autocorrelation time? And if so, how is the autocorrelation time estimated?
So we're basing it on Gong and Flegel, and I would need to check how they're doing that because I haven't, like, reread the paper in a little bit. So I think it is based on autocorrelation, but I'm not, like, I don't think I can give you, like, details on any of that.
Okay, thank you.
Sorry.
I just wanted to say there's a slight irony of the fact that they were using for this between and within ratio. It's sort of like very much out of classical multivariate analysis, and it looked like they chose Gelman and Brooks chose Roy's maximum root back in the day, and you've replaced it with I think Wilkes Lambda or something, or at least it's like very much of that same flavor. And it's interesting because Roy's maximum root's kind of known not to work all that well in multivariate analysis. So I wonder why they chose it in the first place.
Yeah, I wonder too. I wonder what was known in 1998, because maybe.
Certainly, no, that's old. Like that goes back to.
Oh, okay.
That's classical. That's like back to the 50s or 60s or something.
Oh, okay. Yeah, that would be an interesting question to ask.
It's just one of those things. It's just, you look at the formula and it's like, oh, yeah, it's basically like something straight out of classical multivariate analysis. It's one of the ironies of a lot of these diagnostics is that they, I think, kind of demand that you act like a frequentist when you're analyzing, just deciding whether it's convergent or not. But, yeah.
Yeah.
I guess I have a question. I'm just curious. So in your initial, right at the beginning, when you surveyed 100 papers, right, and found this sort of array of different values, right, thresholds, like, was there in those papers, to the extent that you sort of read them, was there sort of reasoning provided for the sort of thresholds that were picked, or was it kind of like, it's like small, around 1.1, a little bit less?
Yeah, they pretty much just reported it, and, like, in the cases where they did choose 1.1, then there was more of that explanation. But for those kind of other seemingly arbitrary ones, like 1.03, then, like, not really justification was given.
Thanks.
I wouldn't be surprised if it was easy to get to those numbers and it was better than 1.1. So it was like, great. So we chose something that was harder and we got it, you know.
Right, like maybe they just ran it for, you know, however many steps and they're like, oh, okay, it just made 1.03. Cool. We'll just say that we ran it till that then. That would be my guess.
Thanks.
Have you talked to Andrew about this?
No. I'm like,
I don't think
know.
I bet he'd be, I don't know. I'm talking to Stan team later today. So
okay.
some of them about it, but I bet he'd be excited. I would like to believe about it. That's great. You know?
From like a thing that I saw, I don't know if that was necessarily true that he was excited about it, but
well, we'll work on
maybe.
it.
I guess I have another question. If nobody else has them, I'm gonna jump in. So I'm curious about computational cost and if that kind of plays a role. You know, in your Titanic simulations, you know, is there sort of like, to what extent does one really have to think about you know, the computational cost of sort of having these using these lower thresholds? I mean, in practice, do you find in your simulations that there's any kind of you know, is it all kind of negligible, the differences, or do you think that that's a concern that makes sense to think about as well?
I think that is a concern because, and I think that's part of why people haven't really like questioned the 1.1, because they're like, well, that's convenient. Like, so it already took me like 3 hours to run till this point, so I don't want to really run any longer. But I think like if you're going to go to all the trouble to like set up your model and collect your data, then like it's probably worth it to still run it for however long it should take.
Yeah, that may be one of the biggest differences between 1997 and now, right?
Yeah,
well, that's true.
It used to take 2 days. Now you can do in 10 minutes or something, you know, it's just, so.
Yeah, we're pretty lucky.
Any last questions? You can also post questions in the chat.
Definitely happy to take them by email later as well if
let me ask
you
a
need some
question
time to brew.
out of curiosity. In the Titanic data, you gave distributions, posterior distributions for various parameters. I wonder how those parameters are correlated in the posterior. So if you survived and you for this anyway, I wonder if you look at that and what they might be.
Yes, we did, and I wish I had like dug up I like started to look at the output again, but I didn't. I don't have like numbers to give you. I don't have like. I wish I had dug in more into that, but I don't have the like actual like covariance matrices ready at this time to like show you.
All right, so I guess let me just ask if there are any sort of final questions. Otherwise, we can wrap up. Okay, well, let's thank Dr. Knudson again for a great talk, and thanks to everybody for attending. So,
thanks everyone.
Everybody. Thanks so much. So I will stop recording now.